Welcome to this course on Applied Electronic Systems. Electronics is at the heart of almost every modern technology. From communication systems and computers to medical devices and industrial control equipment, electronic systems shape the way we live and work. Among these systems, amplifiers play a central role. They are the building blocks of communication, signal processing, and measurement systems. In this course, we will explore the theory, design, and analysis of amplifiers and related circuits. We will learn how to represent and classify amplifiers, how to bias and stabilize active devices like bipolar junction transistors and field effect transistors, how to perform small signal analysis, and how to understand frequency response. We will also examine feedback, stability, and compensation, topics that are essential for designing reliable and high-performance electronic systems. This course is divided into two modules. Module 1, Amplification Basics, Classification of Amplifiers, Transistor Biasing, Small Signal Representation, and Amplifier Analysis. Module 2, Frequency Response, Broadband and Narrowband Amplifiers, Communication Circuits, Feedback Analysis, Stability, and Compensation Techniques. Let us begin with Module 1. Module 1, Fundamentals of Amplification and Small Signal Analysis. 1.1 Amplification and Circuit Elements. Amplification is the process of increasing the strength of a signal without changing its essential form. For example, a weak audio signal from a microphone can be amplified to drive a loudspeaker. Similarly, signals in communication systems are amplified to transmit over long distances. Amplifiers use circuit elements such as resistors, capacitors, inductors, and most importantly, active devices like transistors. The transistor provides the necessary power gain by controlling a large output signal with a smaller input signal. The purpose of amplification is not only to make signals stronger but also to prepare them for further processing, transmission, or measurement. 1.2 Classification of amplifiers. Amplifiers can be classified in several ways. By the type of signal they handle, audio amplifiers, radio frequency amplifiers, or instrumentation amplifiers. By the method of operation, such as voltage amplifiers, current amplifiers, transconductance amplifiers, or transresistance amplifiers. By the mode of operation of the active device, Class A, Class B, Class AB, and Class C amplifiers. These classes describe how much of the input signal cycle the device conducts, affecting efficiency and linearity. By the configuration, such as single-stage, multi-stage, differential, or operational amplifiers. This classification helps engineers choose the right amplifier type for a particular application. 1.3 Representation of an amplifier circuit. An amplifier can be modeled in different forms depending on its function. Voltage amplifier, where the main goal is to increase voltage. Current amplifier, where the goal is to boost current levels. Resistance amplifier, focusing on the ratio of voltage to current, or impedance matching. Transconductance amplifier, converting input voltage into output current. These representations simplify circuit analysis and allow us to focus on the desired performance characteristics. 1.4 Biasing and stabilization of BJTs and FETs. For transistors to function as amplifiers, they must be biased properly. Biasing means setting the initial operating point of the transistor so that it can handle input signals without distortion. For BJTs, biasing involves setting the base emitter voltage and collector current appropriately. Common biasing methods include fixed bias, voltage divider bias, and emitter stabilization. For FETs, biasing requires controlling the gate source voltage to set the drain current. Techniques include self-bias, voltage divider bias, and feedback bias. Stabilization is equally important because temperature changes and transistor parameter variations can affect the operating point. Proper stabilization ensures consistent performance over time and under varying conditions. 1.5 Small signal representation of active devices. Once a transistor is properly biased, we can analyze how it responds to small variations in input signals. This is called small signal analysis. In small signal representation, the transistor is modeled as a linear circuit with parameters such as resistance, conductance, and controlled sources. This simplification makes analysis easier while still capturing the essential behavior of the device in amplification. For BJTs, the hybrid pi model is often used, while for FETs, equivalent small signal circuits are developed. 1.6 Small signal analysis of single-stage amplifiers. A single-stage amplifier consists of one transistor with associated resistors and capacitors. Small signal analysis of this amplifier involves determining parameters such as voltage gain, the ratio of output voltage to input voltage; input resistance, how much load the amplifier places on the source; output resistance, how the amplifier interacts with the load. This analysis shows how the amplifier responds under mid-band conditions, where capacitive and inductive effects can be ignored. 1.7 Multi-stage amplifiers. When a single amplifier stage cannot provide sufficient gain or desired performance, multiple stages are connected. These are called multi-stage amplifiers. The total gain is the product of gains of individual stages. Coupling between stages may be achieved through capacitors, transformers, or direct connections. Multi-stage amplifiers are common in radios, televisions, and other communication systems. Understanding how to analyze multi-stage amplifiers is essential for designing practical electronic systems. Module 1 Summary. In Module 1, we introduce the fundamentals of amplification and amplifier circuits. We examine circuit elements, amplifier classification, amplifier models, biasing and stabilization of BJTs and FETs, small signal representation, and analysis of single and multi-stage amplifiers. With these foundations, we are now ready to explore how amplifiers behave across frequencies, and how feedback and compensation improve performance, in Module 2.